The United States just shattered a record that stood for 131 years. And here is what nobody is saying out loud. The climate event that was supposed to cause this has not arrived yet. The trigger has not fired. What you are looking at right now is the opening act. 60% of the lower 48 states is in drought. Florida is nearly 100% dry. Winter wheat is collapsing in the fields. Lake Powell is sliding toward the threshold where it can no longer generate electricity. The cattle herd is at levels not seen since 1952. And the Super El Nino is still building in the Pacific. Stay with me. Because if the system is already this broken before the forcing event arrives, what happens when it actually pulls? Something is wrong with the timeline. Not the timeline of a single storm or a single dry season or even a single bad year. The timeline of the entire recorded history of American climate. Because right now, in the spring of 2026, the United States is sitting inside the most severe drought ever documented in 131 years of continuous instrumental records. And the event that scientists expected to drive the worst of it has not even fully arrived yet. Let that settle for a moment. The worst on record before the main event. That is the paradox at the center of everything we are about to discuss. And I want you to hold on to it because every single thing that follows, the snowpack that is not there, the cattle herd shrinking to levels not seen since the Truman administration, the reservoirs dropping toward thresholds that should not be reachable yet, all of it flows back to this one central impossibility. The record broke before the trigger fired. Let us start with the data because this story is not built on speculation. It is built on numbers, and the numbers are genuinely alarming. The National Oceanic and Atmospheric Administration maintains what is called the National Centers for Environmental Information Dataset. This is the gold standard of American climate records going back to 1895, when consistent standardized weather instruments became widespread enough across the country to generate statistically reliable national data. 131 years of readings, temperatures, precipitation, soil moisture, every month, every season, stretching back to the tail end of the 19th century. In the first 3 months of 2026, January, February, and March, the United States posted the single driest January through March on record. Not the second driest. Not close to the record itself. Breaking a mark that had stood since 1910. 1910, when the Wright brothers had only been flying for 7 years, when there were 46 states in the Union, when the instruments measuring that drought were less reliable than anything we use today. The fact that 2026 broke a record set under those conditions makes it more striking, not less. If anything, the 1910 number was probably an overestimate of how dry it actually was back then. The instruments had wider error margins. We were measuring less accurately, and we still beat it. Now a single metric can mislead. One instrument, one data set, one way of measuring drought can have blind spots. That is why what happened in the spring of 2026 is so difficult to explain away. Because it is not one metric. It is every metric simultaneously, all pointing in the same direction. The Palmer Drought Severity Index, the PDSI, is one of the most widely used tools in climate science for quantifying drought. It is not simply measuring how much rain fell. It is an integrated model that accounts for precipitation, temperature, soil moisture storage and release, and the atmospheric demand for water. It produces a number. Positive values mean wet conditions. Negative values mean dry. The deeper the negative, the worse the drought. Think of it as a running balance sheet for water where every hot day and every rainless week shows up as a withdrawal. March of 2026 posted a national PDSI value of negative 7.85. April came in at negative 7.56. To find worse numbers anywhere in the record, you have to go back to 1934, the absolute peak of the Dust Bowl, the era of Steinbeck's grapes of wrath, of dust storms that buried entire towns, of topsoil blowing off the Great Plains and landing on ships in the Atlantic Ocean. That is the only frame of reference we have for what the PDSI is currently showing. And even that comparison has caveats we will get to, because the world of 2026 is not the world of 1934 in ways that make this potentially worse, not better. Then there is the coverage number. 60.92% of the contiguous United States was in drought as of the spring of 2026. Nearly 44% of that was classified as severe to exceptional. Those classifications are not vague. Severe drought means crop losses, mandatory water restrictions, and widespread livestock stress. Exceptional drought is the top of the scale. The category where federal disaster declarations happen almost automatically, where aquifers start showing multi-year damage. When you have 44% of the country in that range simultaneously, you are not looking at a regional weather problem. You are looking at something that behaves more like a continental system failure. And here is the part that makes all of this even harder to process. The climate-forcing event that most models expected to drive the worst of these conditions does not fully exist yet. We are talking about El Niño. Specifically, a potentially historic El Niño that some models are projecting could reach what is classified as a super El Niño, with sea surface temperature anomalies in the central and eastern Pacific exceeding 2 degrees Celsius above normal, and some model runs projecting exceedances above 3 degrees. The probability of El Niño conditions developing by mid-2026 sits around 61% in the leading ensemble forecasts. More likely than not. But it has not happened yet. The system is already breaking records without the trigger, before the gun has gone off. Think of it this way. Imagine a boxer who gets knocked down before the fight even starts, just from the walk to the ring. That is where we are. The drought we are seeing right now is not the drought we were warned about. It is the pre-drought, the baseline, the floor. And if the trigger event arrives as forecast, if the super El Niño materializes at the upper end of model projections, then what we are experiencing right now is not the story. It is the setup. Somewhere in Kansas right now, a wheat farmer is watching soil moisture readings that should look like late June showing up in early spring. A reservoir manager in the Colorado River Basin is running projections that keep returning numbers she does not want to believe. A wildfire planner in the Pacific Northwest is looking at snowpack maps showing percentages so low they do not fit the historical color scale on his mapping software. None of them needed a forecast to tell them something was wrong. The land told them first. We just have not been paying attention at the national level because this disaster has no single moment, no one image, no hurricane making landfall on camera. It is the kind of disaster that does not announce itself. It just deepens. And that is the question to carry through everything that follows. If this is what the pre-trigger looks like, what does the peak look like? There is a principle in science that when independent measurement systems converge on the same conclusion, that conclusion becomes very difficult to dismiss. You can argue with one thermometer. You can question one data set. You can point to methodology flaws in one study. But when three entirely separate instruments using three entirely different approaches to measuring the same phenomenon all return the same answer at the same time at the same scale, you are no longer dealing with measurement uncertainty. You are dealing with reality. That is exactly the situation with the drought of 2026. The first system is the most straightforward. Precipitation anomaly data from NOAA. Raw measurement. How much rain and snow actually fell compared to the historical average. No modeling, no inference. Just accumulation gauge numbers from thousands of monitoring stations across the country. January through March of 2026 came in as the driest such period since the record began in 1895. That is the whole sentence. No qualifying clause softens it. The second system is the Palmer Drought Severity Index, the Integrated Water Balance Model. The PDSI does not just ask how much water fell from the sky. It asks how much water the land actually has available, accounting for how much the atmosphere is demanding back through evaporation and plant transpiration. And this is important because the same precipitation deficit that causes moderate drought in a cooler year produces severe drought in a warmer one. The PDSI bakes temperature into the calculation. When it says negative 7.85 in March of 2026, it is saying that the combination of low rainfall and high atmospheric demand has produced a soil water deficit that ranks second only to the absolute worst month of the worst drought in American recorded history. The third system is the United States Drought Monitor, which takes a different approach entirely. Rather than modeling physical water balances, it uses a multi-indicator methodology incorporating precipitation, soil moisture, stream flow, groundwater levels, vegetation health indices, and expert input from local observers on the ground. Then it classifies areas into 5 categories: abnormally dry, moderate drought, severe drought, extreme drought, and exceptional drought, based on observable impacts to agriculture, water supply, and ecosystems. It is the most operationally grounded of the 3 systems because it is not just asking what the models say. It is asking what is actually happening to crops, reservoirs, and rivers right now. In April of 2026, all 3 systems return the same verdict simultaneously. The precipitation record said driest period ever. The PDSI said second worst soil water deficit outside the Dust Bowl. The drought monitor said 60.92% of the lower 48 in drought with nearly 44% in the severe to exceptional range. Not one of these metrics diverged. Not one offered a counter-narrative. This matters because historical droughts often show disagreement between metrics. A regional drought might drive drought monitor numbers high in one part of the country while precipitation anomalies look normal nationally. What is happening right now is something climatologists call continental coherence. The drought is behaving as a single unified system across the entire contiguous United States simultaneously. That is not normal. That is not how drought usually works. There is also what happens when the scale of a phenomenon pushes up against the edges of the measurement system designed to capture it. Climate scientists have a term for this: metric saturation. The drought monitor's most severe classification, exceptional drought, was designed to capture conditions affecting maybe 5 to 10% of the country at most in truly extreme circumstances. When exceptional drought covers nearly a quarter of the lower 48, the classification system starts losing its descriptive power. Words like severe and exceptional were calibrated for a different baseline. They do not fully communicate what is happening when they apply simultaneously to nearly half the country. When everything is a record, records stop feeling like records. When exceptional drought is everywhere, exceptional stops sounding exceptional. And there is the slow disaster invisibility problem. A hurricane has a landfall. An earthquake has an epicenter. There is a moment, a location, a catastrophe that concentrates attention. Drought does not do that. Drought accumulates. It is a debt that builds in silence, day by day, week by week, until suddenly the bill comes due in the form of crop failures and empty reservoirs and fire seasons that start in February. By the time drought is visible enough to generate a news cycle, the damage has already been done for months. The U.S. drought of 2026 may be the most extreme example of slow disaster invisibility in modern American history. Look at any drought monitor map from April of 2026 and let your eyes drift to the southeastern corner of the United States. Florida on a normal drought map should not look like this. The state receives between 45 and 65 inches of rainfall per year across most of its geography. It sits between the Gulf of Mexico and the Atlantic Ocean, two enormous bodies of warm water that normally supply a continuous conveyor belt of atmospheric moisture to the peninsula. It is a humid subtropical climate where afternoon thunderstorms are so reliable in summer that tourists use them to schedule theme park visits. You go inside when the clouds build up at 2 in the afternoon, wait out the rain, go back outside. That is just Florida weather. Except in April of 2026, 98.99% of Florida was in drought. Not 50%, not 70%, not even 90%. Nearly the entire state. Half of Florida was classified as extreme drought, one step from the top of the scale. Roughly 22% had crossed into exceptional drought, the worst classification the drought monitor uses. The category reserved for conditions that are historically rare, economically devastating, and ecologically disruptive even in states that are used to dry conditions. Florida, a state climatologically built around water, where cypress swamps and springs and river systems form the biological foundation of entire ecosystems, was effectively on fire from the inside in April of 2026. The mechanism is called the Bermuda High, and understanding it explains why this drought is so geographically broad. The Bermuda High is a semi-permanent high-pressure system that sits over the western Atlantic Ocean. Under normal conditions, it sits far enough east that its circulation draws warm, moist air northward from the Gulf of Mexico and Caribbean into the southeastern United States, feeding those afternoon thunderstorms and keeping Florida wet. But when the Bermuda High expands and shifts westward, when it essentially pushes its boundaries inland, it creates a dome of high atmospheric pressure over the southeast that changes everything about how the region's atmosphere behaves. High-pressure systems are associated with atmospheric subsidence, air sinking from above, compressing as it descends, warming as it falls. Sinking air is the enemy of cloud formation. Clouds form when moist air rises, cools, and water vapor condenses. When the atmosphere is actively sinking, that process is suppressed. The moisture that would normally be lifted into thunderstorms gets held down, while the sinking and warming air increases the evaporative demand at the surface, pulling moisture out of soils and vegetation and surface water rather than depositing it from above. The result in late 2025 and through the first half of 2026 has been what hydrologists are calling a hydrological inversion, where a region defined by its water surplus starts behaving like an arid system. Wet adapted ecosystems begin experiencing stress that dry adapted ecosystems would normally absorb without crisis. The infrastructure is unprepared. The soils, the vegetation, the river systems, the aquifers, none of them were engineered to handle this. In the American West, where drought is endemic, there are reservoirs designed to hold multi-year water supplies, water rights systems that allocate scarcity, agricultural practices calibrated for low rainfall. In Florida, none of that architecture exists because it was never needed before. The wildfire implications deserve special attention. When drought hits a typically wet ecosystem, the fuel load situation can actually be worse than in a chronically dry one. Arid systems have vegetation adapted to survive dry conditions. It tends to be sparse, low in water content, and those ecosystems have evolved with fire as a regular presence. But subtropical Florida has dense, normally water-saturated vegetation. Palmetto scrub, pine flatwoods, cypress swamps that under normal moisture conditions do not carry fire the way western shrublands do. When that vegetation dries out enough to burn, it burns in environments that are not managed for fire, where communities are not fire-hardened, and where firefighters are not used to running operations at this scale. The Southeast as a whole, not just Florida, was hovering near 99% drought coverage in this period. Georgia, South Carolina, Alabama, Mississippi, all following the same pattern. And this entire pattern was forming before El Niño. The atmospheric configuration producing these conditions in Florida and across the Southeast is a pre-trigger phenomenon. What we are watching in Florida right now is not the drought the forecasters warned about. It is the drought that formed in the absence of the very forcing that was supposed to cause it. There is a concept in hydrology that most people never think about but that controls the water supply for tens of millions of Americans every year. Snowpack as a water savings account. Every winter, precipitation in mountainous regions does not just run off immediately. It accumulates as snow, compressed and stored in high elevations, building a reservoir that is not made of concrete but of frozen water chemistry. As spring and summer temperatures rise, that snowpack melts slowly and continuously, feeding rivers and streams and reservoirs at exactly the time of year when demand is highest and natural rainfall is lowest. It is a natural delay mechanism. Nature's water tower. On April 1st of 2026, 8 western states simultaneously set new all-time record low snowpack values. Not low. Record low. 8 states all at once. Arizona, Colorado, Idaho, Nevada, New Mexico, Oregon, Utah, and Wyoming. This is not a regional anomaly. 8 states covering the full geographical breadth of the American West, from the Mexican border to the Canadian border, from the Pacific coast to the Continental Divide, all measuring less snow water equivalent on the 1st of April than at any point in the historical record. Oregon's number tells you everything you need to know. Its statewide snowpack on April 1st of 2026 stood at 12% of the historical median. Not 12% below normal. 12% of normal. 88% missing. Other states were not much better. Colorado and Utah posting values in the 20 to 30% range. Wyoming and Idaho not far above that. And critically, by the time these numbers were recorded, 75% of SNOTEL monitoring sites, the high-elevation automated sensors that track snowpack across the West, had already reported their snow completely gone, more than a month earlier than the historical average meltout date. That timing matters enormously. When snowpack melts a month early, you do not just lose a month of gradual usable meltwater. You lose the entire smoothing function. Instead of a slow sustained release of water through June and July and into August, you get a brief pulse of meltwater in March and early April, often too fast and too early for reservoirs to fully capture, followed by nothing. Dry riverbeds and dropping reservoir levels for the rest of the season when demand is at its peak. The Colorado River Basin deserves special attention because it illustrates the temperature dimension of this crisis. The basin, which drains portions of Wyoming, Colorado, Utah, New Mexico, Nevada, Arizona, and California, and which supplies water to roughly 40 million people, recorded temperature anomalies of positive 13.7 degrees Fahrenheit above the historical average in the spring of 2026. Nearly 14 degrees above normal. At that temperature departure, precipitation that would historically have fallen as snow falls instead as rain, which runs off immediately without building any storage. Snow that does accumulate melts not just earlier but faster, compressed into a shorter window. And the increased evaporation from soils and surface water accelerates at a rate that follows a well-established physical relationship. For every 1 degree Celsius of warming, the atmosphere's capacity to hold water vapor increases by approximately 7%, which means its ability to pull moisture from the surface increases by the same amount. What 13.7 degrees Fahrenheit of anomalous warmth means in practical terms is that the Colorado River Basin's natural water storage system is not just underfilled this year. It is fundamentally compromised in ways that operate on timescales longer than a single season. And all of this, the missing snowpack, the temperature anomalies, the early melt, the compromised water storage, is happening before El Niño has arrived. The water crisis for the American West in 2026 is not a forecasted risk. It is a locked-in reality. It was decided in February and March when the snow that should have been falling was not. No summer rainfall can undo an absent snowpack. No hurricane making landfall on the Gulf Coast refills the Colorado River. The year's water budget for hundreds of millions of acres of Western agriculture, for dozens of cities, for hydroelectric generation serving millions of households, was written in the absence of snow on mountain slopes that should have been white through May. There is a question sitting underneath everything we have looked at so far that we have not answered yet. Why is 60% of the country dry at once? Why are 8 western states simultaneously hitting snowpack records? Why is Florida, subtropical, ocean-bordered, normally drenched Florida sitting at the top of the drought severity scale? A drought this geographically coherent, this simultaneous across regions with completely different normal climatologies, does not just happen from a deficit of rain. It requires an atmospheric configuration that coordinates dry conditions across a continental scale. And understanding that configuration requires a brief look at some atmospheric physics that sounds complicated but makes immediate intuitive sense once you see it. The atmosphere is constantly in motion with large-scale wave patterns called Rossby waves propagating through the upper levels of the troposphere, the part of the atmosphere where weather systems actually live. These waves have peaks and troughs. Peaks or ridges represent high-pressure systems, areas of descending warming drying air. Troughs represent low-pressure systems, rising cooling wetting air. In a healthy mobile atmosphere, these Rossby waves move eastward, cycling through regions, bringing alternating wet and dry periods that average out over weeks and months to something approximating normal conditions. But Rossby waves can slow down or in extreme cases nearly stop. When a ridge, a high-pressure peak in the wave pattern, locks in place over a region for weeks or months, the atmosphere essentially stalls. The normal cycling stops. Weather systems that would normally move through bringing precipitation get deflected around the stationary ridge rather than through it. Moisture is rerouted away from the locked region. And the persistent subsidence within the ridge keeps the air sinking, warming, and drying over an extended period. Climatologists call this a blocking high. And when it is strong and persistent enough, it can drive drought of a depth and geographic extent that normal weather variability simply cannot explain. In the late fall of 2025 and through the first half of 2026, the atmospheric pattern over North America featured exactly this kind of persistent ridging. A Rossby wave configuration that parked high-pressure dominance over much of the contiguous United States for an extended period, suppressing precipitation, rerouting Gulf moisture, and creating the conditions for a drought that established itself not just in one region but across the entire country simultaneously. There is growing evidence, still somewhat contested but increasingly difficult to ignore, that the weakening of the jet stream itself, potentially connected to reduced equator to pole temperature gradients driven by amplified Arctic warming, may be making these slow stuck wave patterns more common. A more sluggish jet stream produces more persistent blocking patterns. More persistent blocking produces more prolonged droughts. The pattern lock explains how a drought this geographically coherent formed before El Niño arrived. The pre-existing atmospheric configuration, the stalled ridge, the deflected moisture, provided the structural scaffolding for record-breaking drought conditions to establish themselves during what ENSO forecasters were classifying as a transitional neutral period. El Niño did not create this drought. It may be about to amplify it. The drought was already here, already at record scale, built on an atmospheric foundation that required no tropical Pacific forcing at all to produce the worst conditions in 131 years of records. Drought and heat are not the same thing, but they are deeply recursively connected in ways that make 2026 fundamentally different from every major American drought that came before it. There is a thermodynamic relationship called the Clausius-Clapeyron equation. You do not need to understand the mathematics. The concept is what matters. For every 1 degree Celsius that air temperature increases, the maximum amount of water vapor the atmosphere can hold increases by approximately 7%. This means that warmer air has a greater capacity to pull moisture from surfaces, soil, water, vegetation, through evaporation. Warmer air is thirstier air. The same rainfall deficit that would have produced moderate drought conditions in a cooler climate produces severe or exceptional drought in a warmer one because the atmosphere is demanding back more of the water it receives. In the first quarter of 2026, the United States experienced not just its driest January through March, but temperatures significantly above historical averages, this during what was technically a La Niña period, which typically drives cooler conditions across much of the country. The fact that temperatures remained persistently above normal even during a typically cooling phase tells you something important about the underlying trajectory of the thermal baseline. The cool phase of the natural Pacific cycle did not produce the cooling it should have because the background warming trend has moved the baseline far enough that even a typically cooling influence fails to pull temperatures down to historical norms. There is an additional layer to this heat story that remains scientifically contested but is generating significant discussion in climate research circles. In January of 2020, the International Maritime Organization implemented sulfur emission regulations for global shipping, dramatically reducing the sulfur aerosols being released by the global commercial shipping fleet. Sulfur aerosols in the atmosphere act as cloud condensation nuclei and have a cooling effect. They reflect incoming solar radiation back to space before it reaches the surface. Some researchers have argued that the removal of these aerosols is revealing a warming that was always present in the greenhouse gas forcing but was being partially offset by the aerosol cooling effect. The underlying physics is real. Sulfur aerosols do cool the climate and we significantly reduced them in 2020. What is less certain is the magnitude of the effect. It is worth knowing this possibility exists and that if the researchers are right, the background warming amplifying this drought is higher than most mainstream projections accounted for. What is not debated is the drought accelerating effect of heat. There is a measurement tool called the Evaporative Demand Drought Index, which specifically quantifies the atmospheric thirst component of drought rather than just the precipitation deficit. Its values across the American West and Southeast in the spring of 2026 have been running at historically extreme levels, driven by the combination of below normal precipitation and well above normal temperatures. This combination produces what researchers call flash drought, a drought development pathway that can take conditions from near normal to severe in a matter of weeks rather than the months that classical precipitation deficit drought requires. Flash drought is particularly damaging to agriculture because it outpaces the adaptive capacity of both crops and farmers. By the time soil moisture monitors show a problem, the crop stress has already exceeded the threshold where yield loss is locked in. The heat amplification means that the drought we are currently experiencing is more severe at any given precipitation deficit than an equivalent drought in a cooler climate would have been. The same rainfall shortfall that produced the droughts of the 1950s or the 1980s would in the warmer atmosphere of 2026 produce substantially worse soil moisture deficits, substantially worse reservoir drawdowns, substantially worse crop stress. The system is pre-amplified before El Niño adds its additional forcing to the picture. Most people think about drought the way they think about a bank account. You have a balance your soil moisture. Rain makes deposits. Evaporation and plants make withdrawals. When the balance hits zero, you are in drought. When it rains again, the balance recovers. Simple enough. Except the real relationship between soil and atmosphere is not a bank account. It is a thermostat. And once you understand that, the self-reinforcing character of this drought becomes much clearer. When soil moisture is adequate, a significant portion of the incoming solar radiation at the surface goes into evapotranspiration, the combined process of water evaporating from soil and transpiring through plant leaves. This phase change of liquid water to vapor is an energy-consuming process. It absorbs heat that would otherwise go into warming the surface and the atmosphere above it. Wet soil and healthy vegetation act as natural air conditioning. They moderate temperatures. They maintain humidity. And critically, they contribute moisture to the lower atmosphere that can eventually condense and form clouds. Clouds that reflect incoming radiation which further moderates surface temperatures. Now remove the soil moisture. Remove the vegetation water content. Suddenly, instead of energy going into evapotranspiration, it goes directly into sensible heat, the warming of the surface and the air above it. Temperatures spike. The boundary layer of the atmosphere becomes hotter and more turbulent. The humidity that normally helps cloud formation drops. The clouds that would have formed to provide cooling and eventually precipitation do not develop. More solar energy reaches the surface unimpeded. Temperatures climb further. Soil moisture depletes faster. This is what researchers have documented as soil moisture-atmosphere coupling, the feedback loop where dry soil actively promotes further drying by modifying the atmosphere in ways that suppress precipitation. The soil is not just recording the drought. It is participating in it. Once the feedback loop engages, the drought system becomes partially self-sustaining, able to persist and intensify without requiring the external forcing to continue at its initial intensity. The drought carries its own momentum. Vegetation amplifies this further. Plants under severe water stress reduce their transpiration by closing their stomata, the tiny pores through which they exchange gases with the atmosphere. This is a survival mechanism. The plant is trying to conserve what little water remains in its tissues. But in reducing transpiration, the stressed plant stops contributing moisture to the atmospheric column above it, which reduces the local humidity that would otherwise support cloud formation. The vegetation, in trying to save itself, inadvertently contributes to the process that is killing it. This effect scales from microscopic to continental. A single stressed field closes its stomata. A stressed watershed across thousands of square kilometers reduces its collective transpiration. A stressed continent with drought covering 60% of the lower 48 produces a measurable suppression of moisture recycling over an enormous area. The drought of 2026 is large enough that its own surface effects are modifying the atmospheric conditions over a substantial fraction of North America. It is, in a very real physical sense, helping to maintain itself. The wildfire feedback reinforces all of this. When drought-stressed vegetation burns, it releases stored carbon, eliminates the surface cooling provided by live vegetation, darkens the land surface in ways that increase solar absorption, and removes the transpiring plant community entirely for years or decades during recovery. Fire and drought are not separate chapters of this story. They are the same chapter written in different languages. In 2022, a research team led by Park Williams published a study in the journal Nature Climate Change that should have fundamentally changed the way we talk about drought in the American Southwest. Using tree ring records, annual growth rings that serve as a biological proxy for regional temperature and moisture conditions going back centuries, the team reconstructed drought conditions in the southwestern United States going back 1,200 years. Their finding was this. The 22-year period from 2000 to 2021 was the driest 22-year stretch in that entire 1,200-year record. Drier than the 1600s. Drier than the 1500s. Drier than any extended period since the late 800s. And critically, they estimated that approximately 42% of the severity of that drying, nearly half, was directly attributable to anthropogenic warming. Not natural variability. Not Pacific Ocean cycles. Human-caused climate change was responsible for nearly half of the most extreme multi-year drought in over a millennium. This is the southwestern megadrought. And here is the thing that changes the context of everything we have discussed. The conditions we are measuring in the spring of 2026 are not a departure from normal that happened to be severe. They are a continuation and intensification of a megadrought that has been running for over 2 decades. The drought has not started. It never ended. What we are seeing now is the megadrought entering a new phase of intensity, amplified by a thermal background that is warmer than any point in the record the tree rings capture. The comparison to the megadroughts of the 1500s is instructive and frightening in equal measure. Those droughts lasted multiple decades, driven primarily by natural variability in Pacific sea surface temperatures. They were severe enough to potentially have contributed to the collapse of several Native American populations that depended on agricultural systems in the Colorado Plateau. They were devastating events by any historical standard. But they happened in a climate that was on average about 1 degree Celsius cooler than today. In a cooler climate, the same reduction in precipitation produces a less severe drought because the atmosphere is not pulling as hard on surface water. In the 2026 climate, The temperature amplification means that any precipitation deficit drives soil moisture depletion much faster and much deeper than an equivalent deficit would have in the 1500s. Previous megadroughts had one forcing, direct precipitation reduction. Today's megadrought has two, precipitation reduction plus temperature-driven increase in evaporative demand. And they compound multiplicatively, not additively. There is also emerging research suggesting that the precipitation component itself may be shifting toward drier conditions in the southwest as a more permanent structural feature of the regional climate rather than a temporary departure that will eventually self-correct. If that is correct, and it remains an area of active scientific debate, then the concept of drought recovery for the American Southwest may need to be fundamentally reconsidered. Recovery implies a return to a previous baseline. If the baseline has shifted, there is no recovery. There is only the new normal and what lies beyond it. This is the framework within which the spring 2026 records need to be understood. These are not isolated extremes happening in an otherwise healthy system. They are the current expression of a multi-decade systemic shift that is accelerating. Stand in a Kansas wheat field in April of 2026 and the evidence is visible before you pull out a soil probe or check a moisture monitor. The wheat looks wrong. The color is off. The density is wrong. Where there should be green canopy thick enough to obscure the ground, there are gaps, sparse stands, stressed plants whose growth has stalled weeks ahead of schedule. The USDA's weekly crop progress reports tell the quantitative story. By late April of 2026, only 31% of the U.S. winter wheat crop was rated as good to excellent, the two categories that historically correlate with reasonably normal yields. In Kansas, which produces more winter wheat than any other state and functions as the benchmark for the national crop, the majority of acres were rated poor or very poor. Not average, not below average. Poor and very poor, the two worst categories on the scale. The crop condition rating was tracking toward the lowest levels recorded since the severe droughts of the early 2000s. The yield implications are staggering. Regional models were projecting yield reductions of up to 31% compared to the 5-year average. Wheat planting itself had declined to the lowest level since 1919, over 100 years ago, as farmers in drought-affected regions chose not to plant at all in soils too dry to reliably germinate seed, or chose to abandon winter wheat acres that had clearly failed. The calculation of whether to even irrigate, whether to even try to nurse a failing crop toward harvest, became an economic question that many farmers were answering by simply walking away. Soil moisture percentiles across the wheat belt tell you why. In the critical root zone layers, the percentiles tracking moisture relative to the historical range were posting numbers in the lowest 5 to 10% across enormous swaths of Texas, Oklahoma, Colorado, and Kansas. Soil moisture percentile values that low do not just stress crops. They kill them. Below certain thresholds of plant available water, evapotranspiration essentially stops because there is no longer enough moisture for the plant to pull. The crop enters terminal stress from which no amount of subsequent rainfall can fully recover yield losses already locked in through the critical vegetative growth stages. There is a concept in agricultural drought science called the invisible crop failure phase. The period after drought-driven yield loss has already been determined by soil conditions at critical growth stages, but before the visible evidence of crop failure is widespread enough to register in markets or media. The crop has already failed. The farmer knows it. The soil probe knows it. But the satellite imagery still shows green vegetation in the field and the commodity markets have not priced in the full extent of the damage yet. This phase can last weeks, sometimes until harvest begins and the combined yields confirm what the soil was already saying in February. The spring of 2026 appears to be deep inside that invisible failure phase for large portions of the wheat crop. The irrigation question adds another dimension. In the southern plains, the primary irrigation source for drought-stressed crops is the Ogallala Aquifer, one of the largest groundwater systems in the world, stretching beneath approximately 174,000 square miles of the central United States. The Ogallala has been in a state of progressive depletion for decades, drawn down faster by irrigation than it is recharged by natural precipitation. In some areas of Texas and Kansas, the saturated thickness of the aquifer has declined by 50% or more from its historical levels. The buffer is thinner than it used to be. And in a drought this severe, drawing on a depleted buffer at the rates needed to offset a deficit of this magnitude depletes it faster, accelerating the long-term structural problem even as it solves the short-term emergency. The global ripple effects from a 31% yield reduction in American winter wheat are not contained to American consumers. The United States is one of the world's major wheat exporters, and disruptions in American supply flow through global grain markets with effects felt disproportionately in import-dependent nations. When American wheat production falls sharply, global prices rise, and the populations that feel those price increases most acutely are the ones already spending the highest fraction of their income on food. Populations in sub-Saharan Africa, South Asia, the Middle East. A drought in Kansas has humanitarian implications in Cairo and Karachi. That connection is real, measurable, and currently underappreciated in the domestic conversation. In January of 2026, the USDA published its annual cattle report with a number that did not get nearly the attention it deserved. The total U.S. cattle and calf inventory stood at 86.2 million head, the lowest cattle population in the United States since 1952, 74 years. The Truman Administration. Pre-Interstate Highway System America. That is the last time this country had fewer cattle than it does right now. And the reason is directly traceable to drought. Understanding the cattle signal requires understanding how drought drives livestock decisions, because the relationship is counterintuitive until you see the mechanism. When drought hits a ranching region, the first response is forced liquidation. Ranchers sell cattle they can no longer afford to feed. Pasture grasses die or go dormant. Hay prices spike as drought cuts hay production across the same regions that cattle producers depend on for feed. The cost of keeping an animal alive through a drought year can exceed the animal's market value. So ranchers sell calves, cows, bulls. They go to market, often in waves, driving prices temporarily down as supply surges and then driving prices sharply up in subsequent years as the herd rebuilds. What makes it particularly consequential now is the geography. Approximately 60% of the U.S. cattle herd is located in regions that were in drought as of early 2026. The Southern Plains, the Southwest, portions of the Mountain West, and the Southeast. When 60% of the herd is in drought-affected territory simultaneously, the liquidation pressure is not regional and manageable. It is national and structural. The price spike that follows a liquidation this broad is not a local market correction. It is a multi-year national event that affects every American who buys beef. And here is perhaps the most important aspect of the cattle signal as a drought indicator: the recovery timeline. Rebuilding a cattle herd after a drought-driven liquidation event takes years, not months. Heifers must be held back from market and bred. Calves must be raised to weaning age. The full cycle from breed decision to market weight beef is approximately 3 years at minimum. Even if drought conditions improve dramatically starting tomorrow, the cattle herd would not recover to pre-drought levels for at least 3 to 5 years. The drought's economic impact on beef prices will outlast the drought itself by years, which means the damage being measured in 2026 will be felt at the grocery store in 2028 and 2029, long after the weather patterns may have shifted. This is the critical insight the cattle signal provides about the nature of pre-triggered drought damage. The economic consequences of a climate event can be fully locked in before the event reaches its peak intensity. The herd liquidation has happened. The breeding stock has been sold. The recovery timeline is already set in motion. El Niño has not arrived, but its effects on American food prices, operating through the drought that already exists before El Niño, are already baked into the future. Glen Canyon Dam sits on the Utah-Arizona border. 186 meters of concrete spanning the Colorado River just above what used to be one of the most spectacular canyon systems in North America. Behind it, Lake Powell stretches back for nearly 300 kilometers through the eroded sandstone of the Colorado Plateau. Or used to. Right now, Lake Powell is sitting at roughly 23% of its full capacity. You can see the bathtub ring of bleached sandstone extending far above the current waterline, marking the levels where the reservoir once sat, its height measured in years of decline. This matters for a reason that extends far beyond the aesthetics of a shrinking reservoir. Glen Canyon Dam is one of the primary hydroelectric generation facilities in the American West, providing power to about 5 million people in Arizona, Nevada, Utah, Colorado, Wyoming, New Mexico, and Nebraska. The dam generates power using turbines driven by the pressure of water falling through penstocks, pipes that run through the base of the dam. That pressure is a function of the height of the water above the turbines. Below a certain level, there is not enough pressure differential to run the turbines efficiently. And below a lower threshold, referred to as the minimum power pool elevation of approximately 3,490 feet above sea level, the turbines cannot operate at all. As of the spring of 2026, the elevation of Lake Powell was approaching levels where reduced power generation was already occurring, with trajectory models projecting continued decline through the summer drawdown season unless inflow dramatically exceeded projections. Given the snowpack situation with Colorado and Utah basin snowpack at fractions of normal, inflows dramatically exceeding projections seemed unlikely. The energy-water nexus around the Colorado River is one of the most complex infrastructure dependencies in the United States. It is not just that the river supplies water and power. It is that the water supply and the power supply are coupled in ways that create feedback loops in a crisis. When hydroelectric output drops, the grid has to compensate with other generation sources, typically natural gas or imported power from regional markets. That substitution costs money and may not be fully available during periods of peak summer demand when air conditioning loads across the Southwest are already straining generation capacity. Lake Mead, the lower Colorado reservoir created by Hoover Dam, was sitting at approximately 30% of capacity, a level that had already triggered shortage declarations under the Colorado River Compact framework and initiated mandatory cutbacks to Arizona, Nevada, and Mexico. The cutback tiers built into the compact were designed for a system under moderate stress. They were not designed for a scenario where both major reservoirs are simultaneously well below 25% capacity in the context of record low snowpack inflows. There is a concept in systems thinking called a threshold system. A system that behaves differently above and below certain critical parameter values, and where crossing a threshold can produce irreversible or hard-to-reverse changes in system state. Lake Powell and Lake Mead are threshold systems. Above the minimum power pool, they generate power, store water, and provide a buffer against drought. Below it, they lose their primary function and potentially cannot recover it quickly even if conditions improve, because the reservoir must refill, a process that takes years of above-normal precipitation and runoff to accomplish. The spring of 2026 had both reservoirs and trajectories approaching their critical thresholds, powered by snowpack that had already posted its worst April 1st reading in recorded history. And this is happening before El Niño has arrived. By May of 2026, roughly 1.8 million acres had burned across the United States. A number that would be notable for any point in the year, but that in early May represents 231% above the 10-year average for the same calendar period. 231%. Not 31% above normal. 231% above normal. The fire season has not just started early. It has started at a pace and scale that would represent an active mid-season in a normal year, and we are still before the calendar period when fire season would normally be getting established. The National Interagency Fire Center publishes what it calls a national preparedness level, a scale from 1 to 5 that reflects the overall strain on firefighting resources nationally. Level 5 is full commitment of all available resources. By early May of 2026, the preparedness level had already been elevated to levels that would normally be associated with the peak of the season in late summer. Tanker aircraft, hotshot crews, and suppression equipment that would normally be in pre-positioning and training phases in early May were already being deployed to active fires. The resource pool that the fire suppression system depends on does not scale infinitely. There are a finite number of air tankers, a finite number of trained crews, a finite amount of suppression capacity in the system. When that capacity is committed in May, it is not available in July and August when the season would historically be at its worst. The geographic expansion of extreme fire risk beyond its traditional western domain is one of the most significant features of the 2026 fire environment. The Southeast, as we discussed in the Florida section, has seen drought conditions transform its normally wet-adapted ecosystems into high-hazard fire environments. Florida itself experienced significant wildfire activity in March and April, burning through pine flatwoods and palmetto scrub that had not carried fire of this intensity in years. There is a feedback loop between drought and fire that matters for understanding why drought deepens after fire rather than recovering. When fire moves through a landscape, it changes the soil. Intense heat drives hydrophobic compounds into the surface soil layer, creating a water-repellent crust that actually increases runoff and reduces infiltration. Rain that falls on recently burned terrain runs off the surface rather than soaking in, reducing the groundwater recharge that burned areas would otherwise receive. It can take years for this layer to degrade and for normal infiltration to resume. Burned areas thus continue to contribute less to watershed water yields for years after the fire, compounding the drought's effect on stream flow and reservoir inflows. Fire creates the conditions for the next fire. Drought creates the conditions for fire. Fire deepens drought. The three feedbacks do not run in sequence. They run simultaneously, each amplifying the others. And all of this is happening before El Niño has arrived. The United States does not exist in a climate vacuum. The same atmospheric dynamics producing this unprecedented drought in North America are expressing themselves in different forms across the planet, connected through teleconnection patterns, the atmospheric bridges that link regional climates through shared patterns in the large-scale circulation. India's monsoon forecast for 2026 is running at 92% of its long-period average, suggesting below normal rainfall for a subcontinent of over 1 billion people for whom monsoon failure is not an inconvenience but an existential agricultural event. Indonesia is experiencing an earlier than normal dry season, compressing the agricultural calendar in ways that stress food systems already under population pressure. Southern Africa is in a humanitarian drought crisis that has already triggered international emergency responses. These are not coincidences. They are different regional expressions of the same underlying planetary scale pattern shift. The U.S. drought of 2026 is not a uniquely American story. It is the American chapter of a global story. And that context matters for everything from food price dynamics to geopolitical stability. Because when drought hits multiple major agricultural regions simultaneously, the normal global market buffering mechanisms, buy from elsewhere when your region is dry, start to break down. In 1877 and 1878, the most powerful El Niño event of the 19th century reorganized global precipitation patterns in ways that contributed to simultaneous crop failures across China, India, Brazil, and parts of Africa. The resulting famines killed an estimated 30 to 50 million people, making it one of the deadliest climate-related events in recorded human history. The relevant point is not that today's world faces equivalent mortality risk. Global food systems, early warning mechanisms, and emergency response capacities are vastly better than they were in 1877. The relevant point is the mechanism. A powerful El Niño hitting multiple agricultural regions simultaneously in a context where those regions were already under stress from preceding dry conditions produced outcomes that exceeded what any single region's adaptation capacity could absorb. The stress was too broad, too simultaneous, and too deep for the available response mechanisms to manage. The 2026 situation before El Niño is even fully arrived already shows multiple major agricultural regions simultaneously in drought. The climate system is presenting a structural parallel to 1877 with better infrastructure and worse atmospheric forcing. El Niño is at its most basic a periodic warming of sea surface temperatures across the central and eastern tropical Pacific Ocean. Its effects on global weather patterns are extraordinarily complex, and they operate through mechanisms that are not always straightforwardly bad or straightforwardly good for any given region. El Niño reshuffles the global precipitation distribution rather than simply reducing it everywhere. Some regions get wetter, some get drier. The same event can bring drought relief to Arizona while deepening drought in Australia. For the United States specifically, strong El Niño events have historically been associated with increased winter precipitation in the southern tier of the country while simultaneously warming and drying the northern tier, particularly during the critical late winter snowpack accumulation period. A super El Niño of the magnitude being forecast, with some models projecting Central Pacific sea surface temperature anomalies above 3 degrees Celsius, would represent one of the strongest events in the instrumental record, comparable to the events of 1997 to 98 and 1982 to 83. But here is the paradox at the center of this story. The ENSO-drought relationship is typically framed as El Niño arrives and drought follows. The causal arrow runs from the Pacific forcing to the continental response. What 2026 has revealed is that the system can reach record drought extremes before that arrow fires. The drought we have been describing, the 131-year records, the record snowpack lows, the 99% Florida coverage, the cattle herd at 74-year lows, all of this established itself in the neutral to early El Niño phase before the tropical Pacific forcing had reached the magnitude the historical drought relationships were built on. The lag between El Niño peak and the maximum U.S. drought response is typically 6 to 12 months. If the developing 2026 to 2027 El Niño follows that pattern, its maximum U.S. impact would arrive in the spring of 2027. But the spring of 2026 has already set records. Which means the question is not whether El Niño will cause drought. The question is what El Niño adds to a drought baseline that already exceeds everything in 131 years of records. That is not a question anyone has a clean historical precedent for. Here is the point that does not get discussed enough in drought coverage. The mechanisms that would normally interrupt or break a drought of this scale are also compromised. In the American Southeast, including Florida, one of the most historically reliable drought-breaking mechanisms is the tropical storm and hurricane season. Tropical systems, as they move inland from the Gulf of Mexico or the Atlantic, deliver enormous quantities of precipitation over short periods. A single landfalling hurricane can deposit a year's worth of rainfall equivalent over a drought-stressed region in 48 to 72 hours. Not all of that is usable, but it does reset soil moisture, recharge surface water systems, extinguish fires, and interrupt the atmospheric pattern that has been maintaining the drought. The 2026 Atlantic hurricane season forecast is calling for a below-average season. Below-average hurricane activity is itself an El Niño effect. Strong El Niño events increase upper-level wind shear over the Atlantic, which tears apart developing tropical storms before they can organize into hurricanes. The same Pacific Ocean warming that is driving the drought risk is also suppressing the storm activity that would normally provide the principal drought relief mechanism for the Southeast. This creates a closed-loop drought system for the most severely affected regions. The atmospheric pattern lock suppresses precipitation. The heat amplification accelerates soil moisture depletion. The soil-atmosphere coupling reinforces the pattern. And now the principal relief mechanism, the annual injection of tropical moisture from hurricane landfalls, is projected to be below normal precisely because the same El Niño amplifying the drought is suppressing the tropical activity that would break it. Every door to relief is closing at the same time. In the 1930s Dust Bowl, the relief mechanism, precipitation returning to the plains after the multi-year drought broke, eventually worked though it took years. In the 1950s drought, similar eventual recovery. But in both cases, the relief mechanisms were simply delayed, not actively suppressed by the same forcing event driving the drought. In 2026, the El Niño that is driving the drought risk is simultaneously reducing the probability of the hurricane landfalls that would relieve it in the southeast. The system is not just stuck in dry mode. It is locked in dry mode by the same key that opened it. There is a gap between what is happening and what is being discussed. The drought of 2026 has generated coverage. There have been agricultural reports in trade publications, water management updates from western states, fire weather alerts from the National Weather Service. The data has been published. The records have been noted. But the integrated story, the understanding that all of these individually reported pieces are expressions of a single system operating at an unprecedented level before its main forcing event has arrived, has not broken through to the national conversation in the way its scale demands. The fundamental problem is what disaster researchers call the absence of an event horizon. A hurricane has a landfall. An earthquake has a quake. A volcanic eruption has an eruption. These events have a moment, a before and an after, a location, an image. Drought has none of that. The day the Palmer Drought Severity Index crosses from severe to extreme does not feel different from the day before it. The day the 131-year record breaks looks exactly like the day before it. There is no event horizon, no singular moment that crystallizes the story, no image that conveys the scale. The closest drought comes to producing dramatic imagery is the cracked mud of a dry reservoir bed. And we have seen plenty of those images. But cracked mud does not communicate continental-scale systemic failure the way a floodwater wall moving through a city does. Media fragmentation has compounded this. The agricultural story runs in Farm Bureau publications. The water management story runs in Western regional outlets. The wildfire story appears episodically in national coverage when fires become large enough for aerial imagery. The cattle market story appears in commodity trading publications. The snowpack story appears in outdoor recreation media and Western water management circles. No single coverage venue is assembling all of these pieces into the coherent systemic story they constitute together. The elephant is being examined through a series of very small windows, each of which reveals a different body part and none of which reveals the animal. And then there is the psychological dimension of slow disaster. Human attention systems are calibrated for acute events, not gradual accumulation. We notice sharp changes. We habituate to gradual ones. A drought that deepens by a few percent per week over many months simply does not trigger the alarm responses that a catastrophic flood or fire produces, even though the cumulative damage may be orders of magnitude greater. The story has to compete for attention with crises that are faster, louder, and more visually dramatic, even as its aggregate impact grows larger. Anytime something this large unfolds this quietly, the human instinct is to look for something hidden behind it. Not just a cause, but an intentional cause. A lever someone is pulling, a system someone is controlling. And it is worth taking that instinct seriously, at least for a moment, not to dismiss it, not to mock it, but to examine it carefully. Because skepticism, when applied correctly, is how we get closer to truth. The theories tend to cluster in familiar territory. One of the most persistent is tied to the High-Frequency Active Auroral Research Program, better known as HARP, a research facility in Alaska that studies the ionosphere using high-frequency radio waves. In many online discussions, HARP is framed as a kind of atmospheric control system capable of steering weather patterns, creating droughts, or triggering large-scale climate anomalies. Alongside that, cloud seeding programs, which do exist and are used in parts of the United States and around the world, are often interpreted as evidence of broader weather manipulation. Solar cycle arguments suggest that a reduction in solar activity is reshaping global weather patterns in ways that produce drought. And the chemtrail hypothesis, the idea that aircraft are dispersing chemicals into the atmosphere to influence climate, appears here as it does in nearly every discussion involving unusual atmospheric conditions. On the surface, these explanations share a common appeal. They offer something the real explanation does not. Intentionality, a system with an operator, a cause that feels proportionate to the effect. If something this large is happening, then surely something equally large must be causing it. And if that cause is human, then at least it is something that could in theory be stopped. But this is where the physics becomes unavoidable. The atmosphere over the United States is not a small system. Large-scale weather patterns, the kind that shape continental droughts, involve energy transfers on the order of 10 to the 19th joules. These are not abstract numbers. They define the scale at which the atmosphere operates and set the baseline for what it would take to meaningfully alter weather at that level. Now compare that to HARP. At maximum operational output, it transmits approximately 3.6 megawatts of radio frequency energy, about 3.6 megajoules per second, into a small region of the ionosphere hundreds of kilometers above Earth's surface. That is comparable to the output of a large car engine. It is useful for studying ionospheric physics. It is not remotely capable of influencing tropospheric weather systems, let alone locking a Rossby wave pattern over an entire continent for months at a time. The gap is not just large. It is effectively unbridgeable. We are talking about a difference of more than 15 orders of magnitude. The idea that a facility operating at that scale could steer continental weather does not just seem unlikely. It does not align with the basic energy requirements of the system it would need to control. Cloud seeding faces a different version of the same problem. Unlike HARP, cloud seeding is a real documented technology that works by introducing particles into clouds to encourage the formation of ice crystals. Under the right conditions, it can enhance rainfall or snowfall modestly, typically on the order of 5 to 15%. But the key phrase is under the right conditions. Cloud seeding requires clouds that already contain sufficient moisture and are already on the edge of producing precipitation. In the current drought scenario, the atmospheric pattern driving this event, the persistent high-pressure subsidence associated with the displaced Bermuda High and the stationary Rossby Ridge, actively suppresses cloud formation. Air is sinking rather than rising. Moisture is being diverted rather than accumulated. There are no clouds to seed. What all of these theories share is not just a mismatch with the physics, but a mismatch with the data. They attempt to explain a system-wide pattern using mechanisms that either lack the necessary scale, the necessary reach, or the necessary evidence. And this is where the real explanation comes back into focus, not as a single cause, but as a convergence of multiple well-documented processes that reinforce each other. The atmospheric pattern itself is observable in real time through satellite data and atmospheric reanalysis models. It is not hidden. The heat amplification effect is a direct consequence of thermodynamics described by the Clausius-Clapeyron relationship and has been understood for over a century. The soil moisture feedback loop has been quantified in multiple independent studies. The long-term megadrought in the Southwest has been reconstructed using tree ring data extending back more than a millennium. None of this requires hidden technology. None of it requires coordinated intervention. It requires only that the climate system behaves according to the physical laws that govern it. In a way, that is what makes the situation so difficult to process. The conspiratorial explanations feel dramatic, but they are also comforting in a strange way. They imply control. They suggest that if the cause were identified, it could be turned off. The real explanation offers no such reassurance. It describes a system that is evolving under its own internal dynamics, influenced by long-term changes in temperature, atmospheric circulation, and land surface feedbacks. And perhaps most unsettling of all, it explains how we arrived at a moment where a 131-year record can be broken not at the peak of a known climate event, but in the quiet period before it fully begins. That does not require a hidden hand. It requires a system that has already changed enough that its extremes no longer wait for a trigger. Every major drought in American history leaves behind a kind of blueprint. Not a perfect map of what will happen next, but a set of patterns, warning signs, and consequences that can be compared against the present. When something like 2026 begins to unfold, the natural instinct is to reach backward and ask whether we have seen this before, and if so, how bad did it get? The most obvious reference point is the Dust Bowl of the 1930s. The Palmer Drought Severity Index values being recorded in early 2026, a March reading of -7.85 and an April reading of -7.56, sit just below the most extreme months of 1934 and 1936 in the entire instrumental record. In terms of raw index values, this places the current event in the same category as the worst drought ever documented in modern U.S. history. The geographic footprint is comparable as well. But this is where the comparison breaks down in ways that matter. The Dust Bowl occurred in a climate that was significantly cooler than the one we live in today, roughly 1 degree Celsius cooler on average. That difference might sound small, but in atmospheric physics it is not. Through the Clausius-Clapeyron relationship, every degree of warming allows the atmosphere to hold about 7% more water vapor, translating into faster drying of soils, greater stress on vegetation, and more aggressive depletion of surface moisture under the same precipitation conditions. The Dust Bowl, as extreme as it was, represents a lower bound scenario in a cooler system. It tells us what drought looks like without the modern heat multiplier fully engaged. There is another critical difference. The Dust Bowl unfolded as a relatively discrete event. It was catastrophic, but it was not layered on top of a decades-long background drought. In contrast, the current situation is emerging within the context of a multi-decade dry period in the American Southwest, a megadrought that has already been identified as the most severe in at least 1,200 years. That background state matters because it reduces the system's resilience. Reservoirs are already low. Soil moisture deficits are already established. Vegetation has already been stressed across multiple seasons. In 2026, the drought is not starting from neutral conditions. It is building on an already depleted system. The long-duration megadroughts reconstructed from tree ring data, particularly the ones spanning roughly 1500 to 1560, show that the climate system is capable of sustaining drought conditions for decades. But those droughts occurred in a climate system not being influenced by elevated greenhouse gas concentrations. The baseline temperature was lower. The heat-driven amplification of drought was not operating at the same scale. In other words, the same precipitation deficits would have produced less severe soil moisture depletion and less severe ecological stress. When you line up the closest historical comparisons and examine them carefully, something uncomfortable emerges. Each one overlaps with the present in meaningful ways. Each one explains part of what we are seeing, but none of them fully contains it. The deeper you go into the comparison, the more it begins to look like 2026 is not a repeat of anything. It is a combination of multiple historical extremes layered together in a way that has not existed before. Record-breaking instrumental drought. Region-wide snowpack collapse. A multi-decade megadrought already in progress. elevated baseline temperatures amplifying every moisture deficit, a pattern-locked atmosphere preventing relief, and a major climate-forcing event, El Niño, still building in the background. This combination is new, and when you are dealing with a system that has no precedent, the question of how bad it can get becomes much harder to answer. When that is the case, the question of where the upper limit lies does not have a clear answer. Let us return to where we started, because the place we started is also where the entire story keeps circling back. The United States has broken a 131-year drought record. Not edged past it, not tied it. Broken it. The Palmer Drought Severity Index is posting values second only to the worst months of the 1930s Dust Bowl. 60.92% of the contiguous United States is in drought. Nearly half the country is in severe to exceptional drought at the same time. Florida briefly reached nearly total drought coverage. 8 western states hit all-time record lows for April 1st snowpack simultaneously. The cattle herd is at its lowest level since the early 1950s. Wheat conditions are collapsing across the plains. Reservoirs designed to buffer variability are approaching thresholds that were never meant to be approached. Fire activity is running far ahead of schedule. And the hurricane season, one of the few natural mechanisms that can interrupt a southeastern drought, is expected to underperform. All of that is already happening. And the most important part of the story, the part that turns this from a bad year into a potentially historic inflection point, is that all of it is happening before the system receives the forcing event that historically would explain it. Before El Niño. Most of what we think we understand about drought risk, especially in the United States, is built around timing. There is an assumed sequence. First, the large-scale climate signal shifts. Then the impacts unfold downstream. The signal comes first. The response follows. That ordering is baked into forecasts, into agricultural planning, into water management, into disaster preparedness. It is the invisible calendar that organizes how institutions think about risk. What we are seeing in 2026 breaks that sequence. The impacts are already here. The records are already broken. And the signal that was supposed to explain them is still forming in the background. It is like hearing the sound of something shattering in the next room, glass hitting the floor, something heavy collapsing, and then a few seconds later, hearing the object that caused it actually hit the ground. Cause and effect have swapped places. The system is behaving out of order. So the question that follows is not rhetorical. It is a real unresolved technical question. What happens when the forcing actually arrives? El Niño, in simplified terms, redistributes energy and moisture across the planet. It shifts storm tracks. It alters pressure systems. It changes where rain falls and where it does not. And crucially, it does all of this on top of whatever baseline conditions already exist. That baseline right now is not neutral. It is not even moderate. It is already at the edge of the historical envelope. So you are not layering El Niño onto a normal system. You are layering it onto a system that is already operating at record stress. That is where the idea of compounding becomes critical. Think of the drought not as a single event but as a network of interconnected systems. Soil moisture, agriculture, reservoirs, energy production, wildfire dynamics, groundwater ecosystems. Each of these systems has its own thresholds, its own response times, its own feedback loops. Under normal conditions, those systems can absorb stress. They bend but they do not break. But when multiple systems are stressed at the same time, they start interacting. Agriculture fails. Reservoirs drop. Hydroelectric generation declines. Energy costs rise. Grid stability becomes fragile, especially during heat waves which are themselves intensified by the same drought conditions. Groundwater is drawn down to compensate for surface water losses, reducing future water availability for decades. Wildfire removes vegetation, alters soil hydrology, and deepens the drought that fueled it. These are not separate problems. They are linked. Each one feeds into the others. And they all started intensifying before the primary forcing event arrived. That is what makes this moment so difficult to interpret using historical analogs. The Dust Bowl shows us what extreme drought looks like when agriculture collapses and soil erosion becomes catastrophic. But it happened in a cooler climate. The southwestern megadrought of the 1500s shows us what long-duration dryness can do to ecosystems and societies. But it occurred without modern infrastructure, without globalized food systems, and without anthropogenic warming amplifying the baseline. The late 19th century El Niño shows us how global climate synchronization can lead to widespread famine. But it unfolded in a fundamentally different climate system. Each of these analogs is like a single lens. Useful, informative, but incomplete. What we are seeing now is multiple lenses overlapping. And when you try to project forward from that, the uncertainty is not just about how bad it gets. It is about how the system behaves under conditions it has not experienced in the modern observational era. Climate models are powerful tools, but they have limits. They are very good at capturing average behavior, trends, and large-scale patterns. They are less precise at capturing extremes, especially when those extremes are driven by feedback loops that operate at smaller scales or involve complex interactions between land, atmosphere, and human systems. The feedbacks that matter most in a situation like this, soil-moisture coupling, vegetation stress, fire-atmosphere interactions, are among the hardest to model accurately. They are nonlinear. They can amplify rapidly. And small differences in initial conditions can lead to large differences in outcomes. That creates what is known as upper tail uncertainty. Not just uncertainty about the average outcome, but uncertainty about the worst-case scenarios. And in many cases, the distribution of possible outcomes is skewed. There are more ways for things to get worse than there are for them to unexpectedly improve. So when you ask what this looks like 6 months from now or what it looks like a year from now, the honest answer is not a single projection. It is a range of possibilities with a long tail extending into outcomes that we do not have clean historical precedents for. And that brings us back to timing, because timing determines response. If the worst impacts of a drought arrive after a clear signal, after El Niño fully develops, after forecasts converge, after warnings are issued, there is a window. Not a perfect one, but a window. Farmers adjust. Water managers act. Emergency systems prepare. But if the impacts arrive before the signal, that window narrows or disappears entirely. Decisions are still being made. But they are being made under assumptions that may already be outdated. Farmers are deciding what to plant or whether to plant at all based on soil conditions that are already extreme. Ranchers are deciding whether to hold cattle or liquidate herds, knowing that rebuilding takes years. Water managers are balancing short-term needs against long-term sustainability without knowing how much worse the inflow deficit might become. These decisions do not happen in headlines. They happen quietly in offices, in spreadsheets, in conversations that never make the news. But they shape the outcomes that will be visible months or years from now. And they are being made in a context where the baseline has already shifted beyond anything in the historical record. There is no clean historical blueprint that tells us exactly how this ends. And that, more than any individual number, more than any single record, more than any one metric on any one monitoring dashboard, is what makes this moment different. We are operating in conditions that are, in the most literal and technical sense of the word, unprecedented. Not as a rhetorical flourish. As a description of reality. The developing El Niño, the one that forecast models increasingly agree is likely to form and may become very strong, has not crossed the thresholds that historically trigger its most significant global impacts. The atmosphere-ocean coupling that defines a mature El Niño is still in progress. And yet the United States is already sitting inside drought conditions that by multiple independent metrics are the worst in the continuous instrumental record. So the question that remains, the one that sits underneath all the data and all the models and all the historical comparisons, is not whether this is significant. That is already clear from every instrument in the system. The question is what this becomes. If this is the beginning, if this is what the system looks like before the trigger fully fires, then what does the peak look like? That is not a question with a clean answer. Not yet. And maybe not until we are already on the other side of it, looking back, trying to understand the moment when the records started breaking before they were supposed to. Realizing that that was the signal. Not the El Niño. Not the official forecast. The data itself. Arriving early. Arriving quietly. Without an event horizon. In a drought that does not look like anything until suddenly it looks like everything.